Here we'll learn how transmembrane proteins import into the ER and embed themselves in the ER bilayer. To begin, start a table to learn the two types of proteins that enter the ER. Denote that they are water-soluble proteins and transmembrane proteins, which add to the ER's phospholipid bilayer. Both types have signal sequences that direct them to the ER. Here we'll focus only on transmembrane proteins, which import co-translationally. Ribosomes continue synthesizing them as they cross the membrane. To begin, return to our table to learn the different types of membrane proteins. Denote that they include the following: Type 1 membrane proteins, which have a signal sequence at their N-terminus and an internal stop transfer sequence. Type 2 membrane proteins, which have an internal signal sequence instead of a terminal one. Type 3, which also have an internal signal sequence instead of a terminal one, will distinguish them from type 2 proteins shortly. Type 4, which are multipass membrane proteins that have multiple hydrophobic regions embedded in the bilayer. We'll focus on a 2-pass protein, which has an internal signal sequence and a stop transfer sequence. We'll illustrate how each of these proteins inserts into the membrane. Let's start with type 1 membrane proteins. First, draw an ER membrane with a translocon and a membrane-bound signal peptidase. The translocon is a channel through which proteins enter the ER lumen. Label the cytosolic and luminal sides of the membrane. Next, draw a ribosome bound to the cytosolic side of the translocon. Show that it's translating an mRNA transcript. Now draw a nascent protein emerging from the ribosome and entering the translocon. This is known as co-translational import. The protein threads through the translocon as it's synthesized. Show that the protein has an alpha helix domain and a signal sequence that binds the translocon. The signal sequence functions as an address label and directs the growing protein to the ER membrane. Label the alpha helix stop transfer sequence. It's an internal sequence that is hydrophobic, just like the signal sequence. Indicate that this is step 1. The stop transfer sequence stops the transfer of the nascent peptide through the translocon. Note that stop transfer sequences are always hydrophobic transmembrane domains. In step 2, indicate that signal peptidase cleaves the signal sequence. In step 3, show that this allows our stop transfer sequence to exit the translocon laterally. Even after this occurs, the ribosome continues translating until the remainder of the protein is synthesized before dissociating from the membrane. Finally, label the luminal side of the protein as NH2, which is its N-terminus, and the cytosolic end as COOH, which is its C-terminus. Now let's illustrate type 2 protein insertion. This time draw a cytosolic ribosome translating an mRNA transcript. Show that the emerging protein has an internal signal sequence which functions as an address label, just like the terminal signal sequence in our type 1 diagram. Label the protein's N-terminus. Now show the ribosome, mRNA, translocon complex in the ER membrane. Illustrate that the internal signal sequence acts as an alpha helix domain and binds to the translocon. This transmembrane alpha helix anchors the protein in the membrane. Finally, use an arrow to show that, much like the stop transfer sequence in our type 1 diagram, the internal signal sequence exits the translocon laterally in the membrane. Indicate that this time, signal peptidase does not cleave the protein. Finally, label the C-terminal and N-terminal ends. This membrane topology makes this a type 2 protein. Now let's show how type 2 proteins differ from type 3 proteins. Draw another portion of the ER membrane with a translocon embedded within it. This time, draw the protein and alpha helix domain in the translocon first. Note that so far this diagram is identical to our type 2 diagram. Here, draw the ribosome mRNA transcript on the right side of the translocon. Now label the emerging end of the protein as its N-terminus. Show that the alpha helix domain exits the translocon laterally. Again, no cleavage occurs here. Now label the N-terminus and the C-terminus of the protein. It has the opposite topology of a type 2 protein. Let's use a stitch analogy to clarify this concept and introduce type 4 proteins. Draw a needle tied to a spool of thread in the cytosol. Label the needle internal signal sequence and the needle point N-terminus. Label the spool ribosome. Begin with type 2 insertion. Draw a line to represent a piece of cloth. Imagine the cytosol above it and the ER lumen below it. Now imagine that we put one stitch into our cloth. Show that our needle, the internal signal sequence, remains inserted in the membrane and that the needle point, the N-terminus, emerges into the cytosolic side. Now imagine that we pull the remaining thread from our spool through the cloth. Indicate that the free end of the thread in the ER lumen is the C-terminus. Next, let's use the same analogy for type 3. Imagine that we use our needle to stick the cloth just once, instead of making a full stitch. Note that the needle points in the opposite direction of our type 2 needle. Illustrate that we unwind the thread from our spool. Now show that the C-terminus remains in the cytosol and the N-terminus is in the ER lumen. This brings us to type 4 proteins. Let's use our thread analogy to illustrate one now. First, show that just like our type 2 protein, we thread our needle through the membrane to form a stitch. This time, label the portion of the thread that crosses the membrane stop transfer sequence. Just as in type 1 protein insertion, stop transfer sequences stop the transfer of protein through the translocon. Show that this time we do not pull the rest of the thread in our spool through the cloth. Label the terminal ends of our thread such that both the C-terminus and N-terminus remain in the cytosol. With that imagery, now we can draw a final ER membrane to illustrate an actual type 4 protein. Draw two alpha helices that traverse the membrane. The left helix is a stop transfer sequence, and the right is an internal signal sequence. Draw a line to connect them in the ER lumen. Show that both the N-terminus and the C-terminus extend into the cytosol. Indicate that this is a two-pass transmembrane protein. Type 4 proteins can pass through the membrane many more times. They're not limited to 2 passes. Write that for more than 2 passes, each stop transfer sequence must alternate with a start transfer sequence that restarts the transfer of the protein through the membrane. We'll not draw this here. This concludes our diagram.